One spin in thermal contact with a large spin system. Generalize the preceding problem by considering the case where the system A' consists of some arbitrarily large number, capital N, of spins 1/2, each having a magnetic moment μ0. The system A consists of a single spin with magnetic moment μ0. Both A and A' are located in the same magnetic field B and are placed in contact with each other so that they are free to exchange energy. When the moment of A points up, n of the moments of A' point up and the remaining n' point down. When the moment of A points up, find the number of states accessible to the combined system A plus A'. This is of course just the number of ways in which the capital N spins of A' can be arranged so that n of them point up and n' of them point down. Okay, so let's start with part A. So there are a few things I should basically note here. When the A spin points up, when it is plus, A' has n moments pointing up and n' moments pointing down, and n plus n' is equal to capital M. Therefore, the corresponding total magnetic moment for system A will be equal to μ0. The corresponding total magnetic moment for system A' will be n minus n' μ0, which can also be written as, since n' is capital N minus n, 2n minus capital N μ0. So corresponding to this, for the system A star, which is A plus A', there will be a total magnetic moment m star, which will be equal to n plus 1 minus n' μ0. It can be written this way, or it can be written as 2n plus 1 minus n μ0. Now, in the combined system, I'm going to basically, since this is a generalization of the preceding problem, A star system is still isolated, so the total energy E star, which is E plus E prime, that is equal to minus M star multiplied by B, is a constant. So this must be the case. So since B is not changing, we should have the constraint on the system is that M star, the total magnetic moment, which is the magnetic moment of system A plus magnetic moment of system A prime, must be equal to 2n plus 1 minus capital N μ0, a constant. So this is a constraint. So it can be written as total energy is a constant or total moment is a constant, because that determines the total energy anyway. So also note that the total moment I'm defining in the direction of the magnetic field, which is pointing up. Okay, so in part A, when the moment of A points up, find the number of states accessible to the combined system A plus A prime. So A is already up, so we're looking for in how many different ways can we choose n out of capital N moments. So basically it's also noted here the number of ways in which the capital N spins of A prime can be arranged so that n of them point up and n prime of them point down. So this is the question. Can we choose and arrange basically? So we're looking for the number of combinations. The answer will be for the number of accessible states to the system, which I will denote by omega plus when A is pointing up, number of accessible states when A moment points up. So this is going to be equal to the combinations of capital N moments taken n at a time. So this will be equal to n capital N factorial, capital N minus n factorial. So that's the answer I'm looking for. And let's move on to part B. Suppose now that the moment of A points down. Okay, now I have A spin is pointing down. The magnetic moment of A moment is pointing down. The magnetic moment is minus mu zero. The total energy of the combined system must of course remain unchanged because, as I said, it's isolated. How many of the moments of A prime now point up? How many of them point down? Correspondingly, find the number of states accessible to the combined system. Now, when A points up, because M star is a constant, so M plus M prime must be equal to M star, which is 2n plus 1 minus capital N mu 0. So this must be a constant. So now I have M is equal to minus mu 0. So this will tell me that M prime is equal to 2n plus 1 minus n mu 0 minus M, which is plus mu 0. So it will be 2n plus 1 2n plus 1 minus n mu 0, 2n plus 1 minus capital N mu 0 plus mu 0. So this tells me that M prime should be 2n plus 2 minus n mu 0, which means it is really 2 parentheses n plus 1 minus n mu 0. So that tells me that the number of up moments n has now become n plus 1, and the number of down moments has now become n prime is n prime minus 1. So basically the answer to the question how many of the moments A prime now point up, now we have n plus 1 moments pointing up. So one of the moments flipped. So there is a decrease of 1 and increase of 1. Decrease of 1 in M prime and increase of 1 in N. So that we have 2 times N plus 1 minus capital N times mu 0 as M prime. Now, in how many different ways can we arrange? So this is the question now. In how many different ways can we arrange n plus 1 spins out of capital N? In how many different ways can we arrange? Okay, so now the answer will be given by, so this is basically the scenario For the number of accessible states omega minus, I define as number of accessible states to a system A star, basically, when the single moment of A points down. So that's what I call omega minus. So this will be equal to the number of different ways I can arrange n plus 1 spins out of capital N. So basically that is combinations of capital N objects taken n plus 1 at a time. So this will be capital N factorial, n plus 1 factorial, capital N minus n plus 1 factorial. So that's the answer to part B. Let's take a look at part C. Calculate the ratio P minus to P plus, where P minus is the probability that the moment of A points down and P plus is the probability that it points up. Simplify your answer by using the fact that n is much greater than 1, n prime is much greater than 1. Is the ratio P minus to P plus larger or smaller than unity if n is greater than n prime? The probability of having the spin up moment in system A is basically the number of accessible states to system A star when it is up divided by the total number of accessible states to the system, and the probability of having A moment pointing down is omega minus divided by omega total. So if you look at the ratio P minus to P plus ratio, you would have omega minus to omega plus ratio. So this will be equal to, for omega minus, I had capital N factorial divided by n plus 1 factorial, capital N minus n plus 1 factorial. And for omega plus, I had capital N factorial. Now it's inverse, so it's capital N factorial at the bottom, n factorial, capital N minus n factorial. So you can see that the capital N factorials will cancel. Now if I continue my algebra here, P minus to P plus ratio, this is basically equal to n factorial, capital N minus n, capital N minus n minus 1 factorial. And then I have at the bottom n plus 1 factorial. I can write this as n plus 1 times n factorial. And then I can write the next term, capital N minus parentheses n plus 1, as capital N minus 1 factorial. Now you can see that I have the n factorials cancelling, and also capital N minus 1 factorials cancelling. So these disappear. So therefore, I find that this ratio of probabilities is equal to capital N minus n divided by n plus 1. So that's the ratio of the probabilities. So that was the first task, and now the task is simplifying the answer for the case n is much greater than 1 and n prime is much greater than 1. So capital N minus n is basically n prime, and here I have n plus 1. If n is much greater than 1, you will have p minus to p plus ratio equal to n prime over n. Now, is the ratio larger or smaller than unity if n is greater than n prime? And if n is greater than n prime, you would have p minus to p plus ratio less than 1, which means p plus will be greater than p minus. So it will be for n greater than n prime, it will be more likely to have a moment pointing up. Okay. So we have answered all the questions. So let's summarize. We have two systems, A and A prime. When A moment points up, A is plus, A prime has n moments pointing up, n prime pointing down. So total magnetic moment of system A is mu0. Total magnetic moment of system A prime is n minus n prime mu0 because each spin has magnetic moment mu0 in both systems. And the total system is isolated so that the total moment m star 2n plus 1 minus capital N mu 0 must be a constant because total energy must be a constant. So this is our constraint on the system. So when we find the number of accessible states, that's the constraint to consider. So in how many different ways can we arrange n out of capital N moments? What is the number of accessible states to the system when a moment points up? It is combination of capital N objects taken n at a time. And when a points down, the magnetic moment is minus mu0, then it implies that n prime is 2n plus 2 minus capital N mu0, so that the total will still be 2n plus 1 minus capital N mu0. And that implies that, as you can see, when you put it into two parentheses, you have 2 times n plus 1 in parentheses. That means we now have n plus 1 moments pointing up and n prime minus 1 moments pointing down. Now the question is, in how many different ways can we arrange n plus 1 spins out of capital N? That will give us the number of accessible states in the scenario when a moment points down, and that is combination of capital N objects taken n plus 1 at a time. If we take the ratio of these two, we find that the probability of having a moment pointing down divided by probability of having a moment pointing up is capital N minus n divided by n plus 1. Each probability is given by number of accessible states for the corresponding scenario divided by total number of accessible states. So this is due to our equal a priori probabilities postulate. And if n is much greater than 1, capital N minus n is n prime, then you can put here p minus to p plus ratio is n prime over n, and if n is greater than n prime, you can see that this ratio is less than 1, which means p plus is greater than p minus, so it will be more likely to have a moment pointing up.